Today, I'm pleased to present the final project report for the e-commerce and focusing on the topic of spam review detection on Vietnamese e-commerce platform. And throughout the semester, I have explored various approaches to tackle the challenging problem. And in earlier stage of the process, I introduced to deep learning model, namely artificial neural network and recurrent neural network. However, to further extend the accuracy and the performance of the model, I have incorporated two additional model, long short-term memory and convolutional neural network. And one of the key objectives of this project was to optimize the hyperparameter of the ANN, IN, and LSTM model. Hyperparameters play a crucial role in determining the performance and generalization ability of the model. And by fine-tuning these hyperparameters, I aim to achieve higher accuracy and improve the overall performance of the model. And to start today's presentation, let's understand the architecture of the CNN model. CNN are a class of deep neural network that can recognize and classify particular features from images and are widely used for analyzing visual images. Their application range from image and video recognition, image classification, medical image analysis, computer vision, and NLP. CNN has contributed a lot in the field of computer vision and image analysis. And CNN is very useful as it minimizes human effort by automatically detecting the features. For example, for apples and mangoes, it could automatically detect the distinct features of each class on its own. The convolutional neural network is widely regarded as one of the most popular and advanced learning models today. And the network is constructed from the following components. The first layer is for convolution layer. The goal of the convolution layer is to extract high-level features from the raw input information using filter or kernel. A CNN is not limited to just one convolution layer. Typically, the first convolution layer captures low-level features such as X, color, gradient, orientation, etc. With subsequent layer, the architecture is designed to gradually capture high-level features. This enables the network to learn more meaningful information and deeper understanding, similar to human perceive. And the next layer is called pooling layer. The pooling layer is a downsampling operation, typically used after the convolution layer to increase spatial invariance, reduce computation and training time while retaining important features. There are several types of pooling, such as sum pooling, L2 pooling, max pooling, and average pooling. Among them, max pooling and average pooling are the most common form. And the last layer is called fully connected layer. The fully connected layer takes input data that has been flattened, and while every neuron in the current layer is connected to every neuron in the previous layer. In the convolution model, after feature extraction through convolution and pool layer, the data is passed to the fully connected layer to produce the final output relevant to the given task. And with the feature extraction and processing capabilities, CNN can also be used for analyzing other data domains such as text or sequential time series data. And for image data, 2D grid filters are used, while 1D grid are typical explored for data like These are time series. And a basic convolution network model can be described specifically as follows. Is the input kernel convolution 1D max pooling kernel global max pooling, and finally is the output. And this figure and a figure below, and this figure is illustration of a convolution neural network with input as a feature matrix of size 3 times 3 convolution layer and an output where W is the weight in the filter and B is the bias value of the filter. And for the convolution component, W is the light weight and B is the bias of the computing unit for the fully connected component. Suppose that we have a convolutional neural network with the structure so like figure below, where the weights and bias are initialized randomly with the following data sample. And sample data as a three-dimensional matrix is fed directly into the model. The output of a computational unit in a CNN is channelized by the following formula. Output is equal to x times w minus bias, and where x is the value metric of the features to be extracted, w is the weight of the filter participating in the information extraction, and b is the bias of that filter. And from there, the value of the first convolution layer with the first kernel is calculated as follows. And next is the value of the first convolution layer with the second kernel is calculated similar as follows. And this figure illustration of a convolution neural network with the value of the first convolution layer compute. And through the max pooling layer, only the significant value is kept. So the result of the pool layer include only the maximum values of each previous convolution layer. And with the same convolution calculation and fully connected layer computation as mentioned in the DNA section, a convolution model is computed with the following value. Okay, and this is the end of CNN model. So let's continue with LSTM model. And let's begin with an example. A samosa on phone every day. It shouldn't be hard to get that. My favorite cuisine is. And we can easily infer here that the comment is about Indian cuisine. But for the IM model, it is highly likely that it will not be able to predict this correctly due to the word samosa at the beginning of a sentence. As after each backpropagation, the variant value becomes smaller and approach zero, causing the model to lose information about the preceding words, and also known as vanishing gradient. And LSTM are specially designed to address the issue of retaining information from preceding words. They have the ability to capture long-term dependency by incorporating memory cells and gating mechanism. This enables LSTM to effectively store and retrieve relevant information from earlier parts of the input sequence, making them more capable of dealing with this problem. And so let's explore what an LSTM model is. First, let's understand the definition of an LSTM model. An LSTM model is an improvement of INET that allow learning long-term dependency without limiting traditional recurrent neural network. The ability to retain information over long periods of time is an inherent feature of LSTM, and it doesn't require additional training to achieve long-term memory. It has the sequential architecture similar to a standard INET, but the modules have a different structure. LSTM consists of four interacting neural network layers that work together in a unique way. So, how is LSTM different from INA? INA and state in LSTM module include the hidden state and the stealth state. Similar to an INET, the hidden state represents the information learned from previous timestamp and is passed from one timestamp to another. It serves as a form of memory in the LSTM model. And in contrast to an INET, the LSTM introduced the concept of a self-state, which is also referred to as the internal or main memory. The self-state is responsible for storing and carrying information over long sequence. It acts as a conveyor belt, allowing relevant information to flow through while preventing irrelevant information from interfering with the learning process. The hidden state is derived from the stealth state and is used for computing the output of the LSTM model. It captures the relevant information needed for making prediction of further process in the model. In an LSTM model, and there are three main components known as gates: the forget gate, the input gate, the output gate. And these gates are responsible for regulating the flow of information and controlling the state of it within the LSTM cell. And let's begin with the first gate is called forget gate. Forget gate. And this gate decides what information should be thrown away or kept. Information from previous hidden state and information from the current input is passed through the sigma function. Value comes out between 0 and 1. The close to 0 means to forget, and the closer to 1 means kept. And in this figure, we can see that the inputs of the gate is previous cell state and current input feature. The function of this gate is determined with information needs to be forgotten from previous cell state. And next gate is called input gate. First, we pass the previous hidden state and current input into a sigma function that decide which value will be updated by transforming the value to be between 0 and 0. 0 means not important and 1 means important. We also pass the state and current input into the tank function to switch value between -1 and 1 to have regulate the network. For example, Mark is a good singer. He lives in California. Jacob is also a good singer. And the memory of Mark should be removed, and Jacob is the new subject. And we can see the subject had changed from Mark to Jacob. Now let's move to the output gate. The output gate decides what next hidden state should be. Remember that the hidden state contains information on previous input. The hidden state is also used for prediction. First, we pass the previous hidden state and the current input into a signal function. Then we pass newly modified self state to the tank function. We multiply the tank output with the signal output to decide what information the hidden state should carry. And the output is the hidden state, and the new set state and the new hidden state is then carried over to the next time step. And consider the following sentence. Jacob debut album was a huge success. Congrats, and the answer is Jacob. And this the figure for illustrations for updating the cell state. And the input of the cell of this state is previous state of the cell. The current input feature, forget gate, and input gate. The functions of this state is update the state of the cell based on the decision information from the forget gate and input gate. What about computation? It will multiply the information from the forget gate with the previous state of the cell and add it to the information from the input gate, then adjust using the tank function. And the first step is adding new information. And the next step is remove information from previous cell state. And the last one is to calculate the CT. And CT is equal to FT times CT minus 1 minus, uh, minus 1 plus IT times GT, and is the formulas of CT. The next step is core updating hidden state for computing the output. And the input is a previous cell state, the current input features, and previous hidden state. The function of this state is update the new hidden state based on the information from the cell state and input features. It will compute using the output gate to determine the information from the cell state should be passed to the hidden state. Then apply the tank function to the cell state and multiply it with the output gate to generate new hidden state. And after the above step, here is a complete LHTM model. And that is end of LHTM model. And this is the formula to calculate the number of parameters for LSTM structure. And with the design to have higher performance, I have optimized the hyperparameter. And for hyperparameter refers to parameters that cannot be updated during the training of machine learning. They can be involved in building the structure of the model, such as the number of hidden layers, and the activation function, or in determining the efficiency and accuracy of model training, such as learning rate or stochastic gradient descent, the size, the number of epochs, and optimizer. Any contract with hyperparameter parameters are learned through the training procedure, example, weight, and bias. And the hyperparameters are evaluated based on the loss of the model prediction. And the hyperparameters are set on the model, and the model is trained on the data, and the performance of the model is evaluated based on the loss function. These steps are followed indirectly to find the optimal set of hyperparameters. As said earlier, we might or might not end up with a global optimal solution. And with different set of hyperparameters, we will different results. For example, with n layer is equal to 10, neural network is or 128, and learning rate is one uh is these are number. And after with optimizer, the accuracy is 98%. And for deep learning algorithms such as ANN, INN, and LSTM, the hyperparameter to be optimized include the number of layers, the number of units, the activation function, the number of epochs, the learning rate, and the drop rate. And to find the best set of hyperparameter for a deep learning model, we can follow two approaches: manual tuning and automatic tuning. Manual tuning In manual tuning, we manually adjust the hyperparameter based on our domain knowledge and experience. We iterate through different combinations of hyperparameter and evaluate the model performance on validation set. This process requires expertise and a deep understanding of the model and data. Manual tuning can be time-consuming and may not guarantee finding the optimal set of hyperparameters. And automatic tuning involves using automatic technique to search for the best set of hyperparameters. One popular approach is to use libraries such as Keras Tuner, Optuna, or Research and this library provide algorithms to efficiently explore the hyperparameter space and find the optimal combination. They often use techniques like random search, or Bayesian optimization. Automatic tuning can have save time and effort compared to manual tuning and can often find better hyperparameter configuration. And it is the workflow for finding the best hyperparameter. The first step is load data, and then build hypermodel with hyperparameter, and then select tuner research. The next step is tuning to get the best hyperparameter. The next one is building model with the best hyperparameter. And the last step is train model with data. And to get a set of best hyperparameter, I use Keras Tuner. And Keras Tuner is an open source library developed by the Keras team. It provides tools for searching and tuning the hyperparameter of deep learning model, such as architect, the network architecture, the number of layers, and the number of computational units, the learning rate, etc. The Keras Tuner library enables the exploration of various hyperparameter configurations to find the best set of value. It automates the process of hyperparameter tuning and assists in determining the optimal hyperparameter value for a given deep learning model. And in hyperparameter tuning, we often encounter different types of hyperparameter, such as choice, integer, and float hyperparameter. Each type serves a specific purpose and requires different approach for tuning. For example, choice method name is a string. The name is the name of a parameter must be unique for each hyperparameter instance in a search space, and the value is a list of possible value. Value must be in float, string, or bool. All values must be the same type. And the next is float method. The name of this method is a string, and this name it must be unique for each hyperparameter instance in the search space. The min value and the max value have data types that have data type float. Min value is the lower bound range, and the max value is the upper bound of the range. What about the step? Optimal float. The data type optimal float and the distance between two consecutive samples in the range. If left unspecific, it is possible to sample any value in the interval. If sampling is equal linear, it will be the minimum additive between two samples. And if sample is log, it will be the minimum multiplier between two samples. And the last method is in method. The name of this method is a string, and they also and it also must be unique for its hyperparameter instance in the search space. The min value and the max value have the at the type are in integer, and min value is the lower limit of the range exclusive, and the max value is the upper limit of the range inclusive. And the step the data type is also ultimate integer, and the distance is the distance between two consecutive samples in the range, and if left unspecified, it is possible to sample any integers in the interval, and if sample is linear, it will be the minimum additive between two samples. And based on the result, and after using deep learning model, and here is the result static table. The model that were athletic include CNN, LSTM, ANN, and INN. The performance of these models are was set using metrics such as accuracy and one macro score on the training validation and test dataset. And beyond the result, we can see that the LSTM model consistently outperformed the other model in terms of accuracy and F1 macro across all datasets. And it achieved the highest F1 macro score on the training set with 99 is with over 99%, and so competitive performance on the validation and test. The results are approximately 74 and 75%. The LSTM achieved the highest accuracy on the test dataset, with the value is uh, approximately 81.43%. And it can be seen that the model achieve high accuracy and F1 macro on the training data, indicating their ability to learn from the available training sample. However, the performance on the validation and test dataset was slightly lower, and this suggests that the model might benefit from a larger training dataset to further improve their generalization performance. And this is the result of the retention in his team article. In general, the result of the model I use are not as good as the result of the retention article. And in my opinion, the reason may stem from my bad data pre-processing and lack of experience in neural network design. And it's the reference, and that is the end of my presentation today. And thank you very much for your listening.